Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 5, which is Thermodynamic Processes and Cycles, and we are studying the basic Rankine cycle. And we're going to be doing an example problem in this video. As a reminder, our basic power plant model, the Rankine cycle, we're going to start with our numbering system that 1 is the feed to the turbine, 2 is the exit to the turbine or feed to the condenser, then we're going to go 3 is the feed to the pump, 4 goes into the boiler, returning us to state 1, the feed to the turbine. Our equations that we're using as our basic model are going to assume that there is no kinetic or potential energy change throughout, or at least a negligible quantity. We're going to have no heat transfer at the turbine or pump. We're going to have no work at the condenser or boiler, and delta H is going to be used to estimate the work or the heat transfer for each of these. Now we do have an exception for the pump that we can estimate that with negative V delta P because it is a liquid and constant volume. So let's work this problem. We have a utility company that's running on a Rankine cycle with a water boiler that operates at 3 megapascals. Saturated steam leaves the boiler and the condenser operates at 40 degrees C. We want to find the work of the pump and of the turbine, and we want to find the heat transfer at the boiler and the condenser. We'll use those to then find the thermal efficiency and then compare that to the thermal efficiency of a Carnot cycle with the same temperatures. I find it very helpful to organize the given information into a table. Now, it's important that you've identified the states with some sort of symbol. I use the numbers 1 through 4 to indicate each of these, so they're matching the diagram in the previous graph. And I want to translate this information from the problem statement to this table. Now, my column headers are temperature, pressure, quality, okay, what percent is vapor of a saturated mixture, specific volume, specific enthalpy, and specific entropy. In this particular case, the water boiler is operating at 3 megapascals. Our tables are in bars, so let's convert that. 3 megapascals is 30 bars. And the boiler runs between states 4 and states 1. So therefore, 30 bar is going to be my pressure at state 1 and state 4. The second sentence tells us that saturated steam leaves the boiler. So the exit of the boiler is state 1, and saturated steam we designate by using quality of 1.0. The next sentence says the condenser operates at 40 degrees C. So the condenser is between the exit to the turbine and the inlet to the pump. So these are states 2 and 3, and those are 40 degrees C. The rest of the problem statement is telling us what we want to find. So, what do we do from here? The key thing is that anytime we have 2 pieces of information, we know that that means that we have enough information to look things up in the data tables. In this case, only state 1 has adequate information to look things up. So we want to look up saturated steam at a pressure of 30 bar. At state 1, we find that the temperature must be 233.85 degrees C, the volume, enthalpy, and S all given here. Now, we may not need all of this information, but I do find it very helpful to go ahead and, while I'm in the data tables, look up everything that I might possibly need. Okay? But now, what are we going to do with the rest of these? The problem is I don't have 2 pieces of information, but I do know some things about a basic Rankine cycle that I haven't taken advantage of. First of all, the pressure at state 1 and state 4 should be the same. We've already indicated that. The pressure at states 2 and 3 should be the same. We also know that our turbine and our pump should be isentropic. So the entropy at state 1 should be the same as state 2, and the entropy at state 3 should be the same as state 4. We also, however, have one more thing that we can assume, and that is that we assume that the exit to the condenser or the feed to the pump is a quality of 0. It is a saturated liquid. So based on these new pieces of information, I have the entropy and temperature at state 2. I have the temperature and quality for state 3. And once I identify the information for states 2 and 3, I'll be ready to look at state 4. For state 3, this is something easy to look up. It's saturated liquid. So I found the pressure, the volume, the enthalpy, and the entropy. But state 2, this is not either saturated liquid or saturated steam. It's some mixture of the two. So therefore, I need to calculate the quality. The quality is done using the definition. So subtract from the actual entropy the saturated liquid value of entropy. Divide that by the saturated vapor minus the saturated liquid. And so the quality is 0.73. I can use that to estimate V2 and H2, saturated liquid, plus the quality times the difference between saturated vapor and saturated liquid. The volume is 14.274. And the enthalpy, using the same technique, is 1925.2. Now, what about state 4? Since I now know the entropy at state 3 and the pressure, I can look that one up. But this is where it gets complicated. This is a compressed liquid. There's limited utility in really searching too hard for this one, okay? I do know that I can also further assume that the volume of the liquid will not change much. So 0.001008 is an approximate value that will work just fine for these purposes. We have most of our data, so next let's solve for the work and heat transfer from each of our devices. Let's begin with turbine. So the turbine is going to run between states 1 and 2. We can calculate that using the change in enthalpy across this device, H2 minus H1, which in this case is negative 878.4 kilojoules per kilogram. Now, each of these technically is actually a specific value, right? It's per unit mass, but that's so difficult to type, I tend to not write that in, so my apologies for that. But so now I have the amount of work produced per kilogram of flow in the turbine. For the pump, it's going to be similar, right? This goes between states 3 and 4, so it would be H4 minus H3. However, I don't have H4. This is where we get to use our approximation, that this is approximately equal to the volume times P4 minus P3. And those I have. So this is the volume is 0.001008 meters cubed per kilogram. This is 30 minus 0.00738 bars. And I need a conversion factor. 100 kilojoules is 1 bar times a meter cubed. And so now I have that the work of the pump is 3.02 kilojoules per kilogram. Okay, much, much less, right? 3 compared to almost 900 kilojoules per kilogram for the turbine. So therefore, the pump's not going to consume a lot of my power, which was part of our goal by condensing this to a liquid. So I have 3 kilojoules per kilogram, but that now will allow me to come back into this equation and set this equal to 3.02. I know H3, therefore I can calculate that H4 must be 170.5 kilojoules per kilogram. So I calculated that after the fact. Now, I also can calculate the net work, right? I'm just going to add these two. And so the net work is negative 875.4 kilojoules per kilogram. Now, what about that heat transfer? The Q for my boiler is H1 minus H4. I've got all the numbers in the table at this point, including H4. And so this is 2632.7 kilojoules per kilogram. And Q for the condenser is going from 2 to 3. And that is negative 1757.3 kilojoules per kilogram. Now, I recommend doing a first law check at this point. This should always be true, but this is just a way of verifying. And that is the sum of your Q net plus the sum of work net needs to equal 0 for a cycle. And if I add these up, 2632.7 minus 1757.3 minus 875.4, and we indeed get that that's 0. Now, as long as you're, like to the last decimal place, you may get a 0.1 or something like that, consider this to be valid, all right? So I have all of my values of the work and heat transfer. Now we want to be able to solve for the work and the heat transfer. What about calculating the thermal efficiency? The thermal efficiency for a Rankine cycle or for any power cycle is the net work over the heat transfer at the high temperature. In this case, the value of the net work is 875.4. The heat transfer at the high temperature is the boiler, 2632.7. And my thermal efficiency, therefore, is 0.3325, or 33.25% efficient. Okay? It's not really all that impressive, but how terrible is it? Or maybe it's not that bad. Let's compare it to the maximum possible. The maximum possible is for the Carnot cycle, which is going to be 1 minus TL over TH. Remember to work with kelvins, so it's 1 minus 313 over 273 plus 234. Don't want to do that math in my head, sorry. And that's 0.3826 or 38.26%. Okay, so this is the max possible. and we actually got 33%. Now, one thing that's done a lot these days is to do a second law efficiency. Now, a second law efficiency I designate with a Roman numeral 2 as the subscript. And all this is the actual thermal efficiency divided by the maximum that you could have gotten. So 0.3325 over 0.3826. And so this is 0.8691. Okay? So we're 87% of the way to the maximum possible. We're not ever going to get to the maximum possible. And then I have a major caveat. I have assumed all of these are reversible. And even with that, we didn't get as good as the Carnot. And when I get to looking at real life, it's going to get worse, right? So, things that we can check to make sure our answers are right along the way. We can check, first of all, that a second law efficiency is less than 1, or our thermal efficiency will be less than our Carnot efficiency, which is the maximum possible, okay? And we also can check a first law that all of the sum of our Q's and the sum of our W's will add up to 0. So that concludes this example problem. We're going to continue looking at the Rankine cycle and variations and how we might improve it in our next videos.